Okay, I think we are recording right now. Yes. Hello. For those of you who don't know me, I'm Nick. I'm going to be your host this afternoon, the first Dead Physics Society weekly seminar of 2021. This week, we're going to receive Théo Meireles from the Department of Experimental Physics at the FUSP. Théo is a physics undergrad at the Physics Institute of the University of São Paulo, and he has experience in the study of turbulence in magnetically confined plasmas. Currently, he works with quantum optics and atomic physics applied to the manipulation of quantum information at LMCal-USP, and he's going to tell us today what does speed have to do with the size of a burst. Please, Théo.
Well, thanks, Nick, for the presentation. I'm going to be presenting, as Nick said, my work, What Does the Speed Have to Do with the Size of a Burst, which was originally called Size and Speed of Burst at Texas Helimac. That was my scientific initiation project during the time of 2019 to 2020, under the supervision of Dr. Louzada. Well, first, the motivations for the project is in the field of plasma physics, what most people say as the holy grail of plasma physics is achieving and maintaining fusion reactions through the and controlling it with the magnetically confinement process, right? So we use magnets to confine the plasma, and the plasma inside has the fusion process happening, right? But as physicists want to understand the phenomena that we have inside this burst, right? So what we have is we have just a whole process to get there and get the plasma confinement done, right? So then we can achieve the fusion process, right? But as physicists want to understand some of the phenomena that we need to overcome to get there. One of these phenomena that we have is inside the plasma in these devices, we have in the border of the plasma, we have high density coherent structures that propagates convectively in this turbulent region. And this movement degrades the confinement of the plasma. So we have a greater loss of number of particles if we simply consider diffusive phenomenon, right? So this makes it an anomalous phenomenon, right? But there are also strategies to then improve the quality of the confinement, and with that, we will be closer to achieving this goal. So some of these hypotheses to increase the quality of the confinement say that if we have a burst and we break it into a smaller one, it will travel slower, thus increasing the quality of the confinement. So in my work, what I did was to try to find a correlation between the size and the speed of the burst to see if this hypothesis was actually correct. So first, what we do to make this analysis, we use data that comes from Texas Helimac. The Texas Helimac is a plasma confinement device, just the tokamak has, the Helimac has, that makes it interesting for this is that it works at lower temperatures, and it also we have an arrangement of probes instead of only arrangement. We have a great arrangement of probes that can lead us to an idea of the two-dimensional format of these structures that we have there. And also, as it has a smaller temperature, we can leave the probe inside for longer and have more data for the same plasma discharge, right? So what first we do is we have the signal that we measure in a probe. This signal is actually proportional to the density of the plasma. So we are not working directly with the density, but given that this signal is proportional, we simply need to normalize it, and it will be all proportional, right? So here we have in one of its probes the saturation current that I said is proportional to the density of the plasma that we have measured in one probe. But in red here, we have what we detect in the signal as bursts. We say that a burst is a peak of density, but it needs to be the bigger one in certain range of time, so we can't have two too close together. But also, these bursts need to be a certain number of standard deviations above the average of the mean of the density of the plasma, right? And given that in the beginning I have said that these bursts were coherent structures, so as they are coherent, they have some similarities. Even though if you gave a zoom at every burst, they will be very different. if we use conditional analysis methods, we can get the average signal of the burst. And this is equal, and this is what means that they are coherent, that in any device that you have the burst, the average signal should be at least somewhat similar to each other, right? So here we have an example of the average burst. To find the average burst, we simply use the conditional analysis methods, right? And here we can see that it seems to have a growth and a decay as it travels through the probe, that it seems to be something like an exponential. But now with that, what we can do to then find an idea of the position and the format of the burst, as we now don't have an idea of a physical format, but only a signal that it leaves on the probe, what we then do is to use an arrangement of 5 by 5 probes, right? And as we have detected the burst here in the central probe, now with the average of the burst at the time that we have the burst, so now here in this point, right, we can look at the average density in the probes around it. So then we can have an idea of what is the burst format inside the device, right? But what we can also do is then to look at times before and after the moment of the burst, and then we can see that the burst actually propagates inside the machine, right? We can see that it's kind of moving upwards and a little bit outwards. But we still have a problem here that we need to solve, is because we have no quantitative measurement of what is the position of the burst, right? So then what we do to solve this problem is to use this theoretical model that is proposed in this article, that we treat the burst as a Lorentzian. And treating the burst here as a Lorentzian, we can then use the least square method to then make a fit of the two-dimensional format of the burst, right? We're normally used to a simple XY fit of the using this kind of linear regression, right? But here we simply use, because sometimes we forget that the least square method is simply a mathematical representation, right? So it's simply the sum of the difference between your function and your value, and you need to minimize it. So we can do it with any number of variables, right? Sometimes we forget it. But with that, what we found is then the position of the burst. And now one can simply state that what we need to do is then to repeat this process 4 times before and after the movement of the burst. Let's say we make a fit for this time, and this time, and for every other frame, let's say, of the movement of the burst, and then we'll have the positions, the time, and then we can calculate the speed. And we have actually done that. But what we found that is best to do is then to improve the theoretical model by setting these boundary conditions in our fit, right? So in the same way that when we were solving the equation, set these boundary conditions, we put these conditions also in our fit. So then when we are going to solve the equation, we need to take this in this consideration, that our x here actually is like have this linearity, and our decay in time is exponential, because we have also verified this experimentally in our data. And then with that, we apply this to the fit, and what we found was, now that we are not fitting for the positions, we make a fit for the whole movement of the burst. So instead of making an XY fit, or in the other case that we have the a fit for a single frame, we make a fit for the whole movement. So we're making a fit for the movie of the burst propagation, right? So besides the speed, what we also find is this interesting movie that is actually a representation of the entire least square method fit of our data, right? So we can see here that the burst propagates inside the device and have this kind of movement, as we see here. It says propagation. As I said, it seems to go a little bit upwards and also a little bit outwards, right? But now what we have to do is to correlate the speed with the intensity. So what we do now to do that? So to determine the intensity, before we get the average signal of the burst, what we do then is to divide the burst in these four regions of intensity. So we get all the bursts that we find, and we divide. Well, you are between 3 to 4 standard deviations above the average. You go to the first group. You are like 4 to 6 standard deviations above the average, and you go to the other group. We can see here that they are not evenly spaced, right? Because the distribution of the intensity of the burst is an exponential, right? So the probability to find a burst that are 3 to 4 standard deviations above the average is really higher than the probability to find a one that is 10 to 16 standard deviations above the average. So we need to increase the range for the bigger burst, so we can have more, so we can trust our model and our results, because we have enough data to it, right? So we have just like 5 to 6 bursts is not enough, so we need to have a greater number of bursts. So then we repeat this whole process, and what we found is this. I have repeated this process for 2 different plasma discharges, which the difference was the bias. The bias being the difference in potential that we applied in that we have in the plates that we have behind the probes that we use to measure the density of the plasma, right? So the first one, the black one, has no potential, the other one has 8 volts, and the other one has 14 volts. So what we have found for the radial and the vertical velocities is that we have, even though we have greater uncertainties, right? We have no clear correlation. We have no signs for a positive correlation in velocity to the intensity, right? So it doesn't seem to have an increase in speed for an increase in intensity. So in conclusion, the developed method that I have done has shown itself to be efficient in determining what is actually the correlation between these 2 intensities, right? But also, which is even more interesting, is that we haven't verified any tendency for the increase on the burst intensity for an increase in its speed, right? And this is interesting, actually, because this goes against the hypothesis that we have in some of the plasma confinement strategies. We have strategies that we apply a gradient in potential inside the device, and people say that, well, the burst is going to break, thus making it smaller, making it slower, and increasing the quality of the confinement. But as we have seen, it's not actually what seems to be happening, right? So this is actually it. It went faster than I believed to be, but thanks everyone for watching. And if you have any questions, feel free to ask me.
Well, thank you very much, Théo. Is there anyone who would like to start the questions? Well, let me ask you then. I believe you might have said it in the beginning of the presentation, but I was a bit concerned with technical issues. How do the bursts cause trouble for the plasma confinement? I believe you should have said that, but could you repeat?
Yeah, I said it, but I was a little bit nervous in the beginning, so I may have a little bit confused.
I know how it feels like.
So if we have in tokamaks, right, we can see here that we have a toroidal shape of the device, and the plasma follows these lines of magnetic field, right? So we have the toroidal and the poloidal fields. And if you have a cross section of the burst, in the border of it, we have a high turbulence region there. And in there, we have these coherent structures that we call the bursts. The burst, besides having high density, they propagate convectively. So as it propagates convectively, it degrades the quality of the confinement because it leads to a loss of a greater number of particles, because we have a turbulent movement, and the particles like can escape, can hit the walls of maybe hit the walls of the tokamak and stuff like it.
I see.
So this convective propagation is what ruins the confinement, right? It actually ruins the confinement.
Instead of the particles moving as you wish they would, just like circling around the tokamak, they start just bumping on the walls and stuff like that.
Yeah, it can bump it on the walls, but actually what you can have, right, is given that it's have you imagine that it will have loss only for diffusive phenomena, right? But these phenomena can like maybe a particle go out or something. But as you have a convective movement, and you imagine that the hardest part is inside the burst, right? You can have like expelled particles out of the plasma column.
I think I see. Thank you. Are there any questions?
I want to ask you a question about the conclusion. There you say there is a assumption made in confinement techniques that they assume there is a tendency of increasing speed of the burst from increasing in its amplitude. So, yes, but you don't find it in analyzing your data.
Yes, correct.
Right? What are the motivations to these assumptions when you are studying the confinement, the plasma confinement?
Yes, this is not like a really famous assumption or like something that everybody uses, but something that we have is the idea of the gradient, right? Because we can put electrostatic probes that will create a gradient in potential, in electric potential. So if you imagine that we have the particles moving around it, if you have a gradient, then you will have a shear, right? So they have an idea of that this shear would make them smaller and increase the quality of the confinement by making them move slower in the device, right? But what was the original idea that why that will make them slower, I really don't know. But probably because making them slower will probably reduce the turbulence, right? So I believe that is the original idea.
Okay, thanks.
Hi, Théo. It's a bit correlated, my question. Can you go to the previous slide of the conclusion?
This one?
Yeah, so you said that you don't find this correlation that you expected, but I see like, I know I'm doing like a chi-squared by I, but I see like an anti-correlation. Do you think like this is statistically significant?
If you see for the zero bias here, and probably for the vertical speed, it seems like we have actually the opposite, right?
Yeah,
but
exactly.
As we have like a huge uncertainty, but also we need to remember that this here is put in the model experimentally, right? And our idea for uncertainty derives from these assumptions. So even though we have a great uncertainty, it's really hard to say that definitely we have an decreasing speed, right? What we then would need to do is to make the analysis for a larger number of these charges and see if this holds for not only for the Texas Hill market, but maybe for other devices too.
Yeah, maybe you could do like a fit for a line with inclination and also a straight line and feature points and see where the chi-squared is bigger and see what is the favorite model, like a model with anti-correlation or a straight line.
Yeah, but at this point, the chi-squared doesn't really helps much because as we can see here, the chi-square is like is really big, right? Because you have a certain point where the chi-square doesn't say much to you about the fit, right? Because again, this here is a model, right? And we make this fit and we impose these conditions for linearity in the speed. And when we did the other way around, when we had all the positions and the times, you can see that you have a straight line, right? But as the burst moves from a probe to the other, when you are going to solve it, as you need to solve a nonlinear equation, it starts to make some movements, then to move your position more to the side, more to the other. So if you see the positions going, they go linearly, but when they reach a position near to what was the position of a probe, they would have a slightly upward movement and then a slightly downwards movement. So your fit, you can completely trust your results based on the p-square because you have a nonlinear fit, right?
Interesting. And have you tried to use it more number of pixels, more or less numbers?
Of pixels in the...
Yes, in those pixels there.
Oh no, right here we can imagine that every pixel is an arrangement of is a position of the probe, right? So the color
Okay.
is just
Okay, something fixed.
So
by the
this
experiment.
Yes, and inside the device, the bigger arrangement of probes that we have is this 5x5 one. So even though if I want to make like a 7x7, because making it non-proportional wouldn't help at all, but like you have a 7x7 probe, it will certainly give a greater idea. But also, as you have, we could like look at the burst at other regions of the device, and if you have a like a really big one, you can probably even put like two bursts inside the same frame. So it wouldn't help very much.
Okay, thank you.
No, thank you for your questions.
Are there any more questions? Anyone? All right. Thank you very much again, Théo, for your wonderful presentation.
Yeah, it was a little bit fast, right?
Yes, but I think it was excellent. It was you used the time well. It was not too fast nor anything like that. Next week, we are going to receive José Arturo de Toledo Queiroz to talk about the physics of societies. Again, it will be on a Thursday at 2 o'clock on BRT time. And thank you very much for coming. We are going to post this lecture on the DPS YouTube channel. I don't know, today, maybe tomorrow. I'm figuring this out yet. But I think that's it. Thank you very much, everyone. I'm going to end the recording now.